So for the first part, we will put an emphasis on determining the focal length of a few lenses. And we have a range here. These lenses will be labeled 1, 2, and 3, and they have varying focal lengths relative to each other. One has a relatively long focal length, one has a relatively short focal length, and one is somewhere in between. But we want to determine the focal lengths of these lenses by utilizing the optical bench that has a luminous source object. It's a little bit difficult to see, but this has a number 4, and when we turn it on, it's going to look like a number 4. But because of the aperture right now on the camera, it's probably going to be too much. It probably looks like a blob of light. Is that the case? Yeah. So we'll use this as our object, and we'll be using a translucent screen. So you can see the images on both sides of this. And by putting them on the optical bench, we'll be able to use the metric ruler that is on the bench to determine the relative positions of the object to the lens and the screen to the lens, because that's really what we're going to be referring to as these distances. They're always going to be relative to the lens. So in this case, I'll have a short image distance and a large object distance, or a short object distance and a larger image distance. So we're able to move these and position them to try to get an image that forms on the screen, and that'll be important because, as you'll see for the first part in this procedure, we're going to manipulate the lens, the screen, and or the object to try to get an image to form on the screen with each of these lenses. And we'll use the data that we collect for the object distance and the image distance in each case to calculate a value for the focal length, again using the thin lens equation. So we can get started. I'll start with lens 1, and I'm going to put it here on the bench. We'll dim the lights, and I'll turn on my luminous object, and we can get in a position to see what this screen looks like too, if you'd like. And we'll zoom in on it. So you'll note that on the screen, we get some semblance of that number 4 that is our luminous object. And we'll note that it appears that this number 4 is not in focus. It's a little fuzzy. It is inverted. And I can tell you that the image appears slightly smaller in size than the object that is being broadcast. So I'm going to have to manipulate either the object or the lens or the screen. It turns out it doesn't matter because we're going to end up getting an image to form, and what we'll want to do is we'll just want to note what the relative distances are for the object and the image. So as you can see, as I move the lens closer or further back, this image on the screen comes into and out of focus. And it's going to be my judgment to where that needs to be in order to get an image. And I think that this is a good position. I go a little bit further, it starts to get fuzzy. I go back, it's crisp. I go back even further, it's fuzzy again. And so somewhere right in there, I'm getting an image to focus and project onto this screen. It's a real image. It's broadcast onto a screen. We have light that's actually converging to this point. But this is not the focal point of the lens. It's involved. The focal length is involved, but we don't quite yet know what it is until we make a calculation for these distances, the object distance and the image distance. So we'll turn the lights on. And then we'll come and take a look at the relative positions of the lens and the object. So with the object located at the 20 centimeter position and the lens located at the, what do we have there, 78 point? 78.2, I'd say. So about the 78.2 position. The difference between these positions is going to be 58.2 centimeters. And on the other side, the difference between the screen and the lens is going to be, what's this? Yeah, so we're looking at now 30.2, 30.3 centimeters is the distance between the lens and the screen. So we have about, if I'm doing the math right in my head, about 30 centimeters between these two, and about 50 centimeters between these two, and we'll mark those values in our lab notebook. All right, so that's the first focal length. We have our data. That's the first lens, rather, to determine the focal length using the thin lens equation. We'll now use the second lens to try to get it into focus. So we have been able to determine, we measure the values for both the object distance and the image distance for 3 different lenses. And with those values, we can now apply the thin lens equation and determine the focal length, solving for that unknown focal length value for each of those lenses. And we'll record that in our lab notebooks. For the second part, in part 1, what it wants us to do, you'll notice that if you take a look in your lab manuals, that the thin lens equation implies that there are actually 2 locations for an image to form when you have the object and the screen in a fixed position. This isn't often clear to students, but it should kind of make sense that if 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length, then if it works for, say, 1 over 3 centimeters plus 1 over 5 centimeters, that should give you the same as if you had 1 over 5 centimeters plus 1 over 3 centimeters. In other words, you can get an image to form on the screen with the lens at 2 different positions for this setup. So as I have it here, there is an image to form on this screen, and it's probably not going to be able to be picked up by the camera, just by the low light conditions. Notice that at this location, I have a relatively small image distance for a relatively large object distance. Now, if I kind of seesaw that, if I balance that on the other side, then I should be able to find an image when I have a relatively small object distance and a relatively large image distance. And sure enough, you'll see an image form on the screen. So, to put this in perspective, we have an image here with our object, lens, and screen all the way down here. And we also get an image to form right there at about the same distance now that the object was away previously, that we have the screen in this location. So 2 locations will give me an image, though there's obviously something that is substantially different about these. They're both inverted on the screen relative to the object itself, but there is a substantial size difference between what we have when the object distance is small compared to when the image distance is small. Okay, so that last part was using the physical distances between the object and the lens and the screen and the lens to apply the thin lens equation and calculate a value for the focal length. But there's another way that we can also approximate the focal length, and it involves using objects that are relatively very far away. So I'm going to remove the object from our optical bench here, and I'm just going to leave the lens and the screen. In fact, I believe I'll start with our first lens, lens 1. And if you recall from last week, the light rays that are formed from objects that are relatively very far away, so very in quotes, very far away, approximately come in parallel. If they're far enough away from some source, by the time they reach all the way down here, they're coming in approximately parallel to each other. And so these light rays are coming in parallel, they're going to hit this converging lens, and they're going to refract and start to converge to a single point. Well, if you take a look at the thin lens equation, the portion of that equation that accounts for the object distance, 1 over the object distance, well, that fraction starts to blow up in the denominator because the object distance is really far away. So what's 1 over 1? It's 1. What's 1 over 10? 0.1. What's 1 over 100? 0.01. As that denominator gets larger and larger and larger, that whole portion of the thin lens equation, 1 over the object distance, blows up in the denominator, like I said, and it almost vanishes. It goes away. 1 over something really large is very close to 0. And so what you're left with is 1 over the image distance is equal to 1 over the focal length. Therefore, the image distance is approximately equal to the focal length. So this is an approximation method. And we're going to use it to compare to the values that we calculated using the thin lens equation previously. So the good news about this is I just need to get something that's really far away into focus from out the window. I've got blue sky, white cloud, green grass, and we're going to see if we can get an image here. But we'll need to lower the lights to see if we can get something to form here on the screen. There we go. So I'm getting a really good image here. And again, I always test. I go a little bit forward, it's fuzzy, I bring the screen backward, it's fuzzy again, and I want to get it so that I can get as many of those details nice and crisp in there. I'm getting a color image that is formed by a converging lens taking parallel light rays, closely parallel light rays, and converging them onto the screen. This distance is a very special distance because it is very close to being the focal length. The light that comes in parallel to a converging lens, parallel light rays that come into a converging lens, will always pass through the focal length. And so for light that's almost parallel, it's going to come pretty darn close to going through the focal length, which is approximately right here at this location. So I simply need to find the distance between these two, and I'll record that distance. And for my number 2 lens, in order to get this into focus, I note that I have to come a little bit closer to get that image to form. And yet it seems a little more intense. So for my 3rd converging lens, the focal length is so relatively short that we can't quite get an image of what it looks like from the front side. But, like I said, this is a translucent screen, so you should be able to see when that image forms. So I get 73.1. In your lab manual, in your lab report rather, you're going to edit an image of a relatively far object from the lens, and you'll edit that image to show how parallel light comes in, hits a converging lens, and then forms an image on the screen. And so hopefully you can relate what you've seen just now to what you'll be doing there to kind of get an idea of how it is that we use this approximation method to determine the focal length for a converging lens.